Good day, everyone. On behalf of the Department of Statistics at the CUHK, I would like to extend a warm welcome to all of you for joining us today for our presentation on the mean value theorem. Let's begin by introducing the topic of our presentation, which is the mean value theorem. This remarkable theorem holds great significance in the field of calculus as it serves as a foundation for the proofs of many other theorems. Essentially, it establishes a connection between the net change of a function over an interval and the possible values of its derivative on that interval. Before delving into the details of the mean value theorem, it would be helpful to first explore its special case known as Rolle's theorem. Now, let's talk about Rolle's theorem. This theorem states that if a function satisfies certain conditions, then there exists a number c where its derivative is equal to 0. In other words, the function has a critical point within that interval. To apply Rolle's theorem, we need to satisfy three conditions. Firstly, the function must be continuous on a closed interval. Secondly, it must be differentiable on an open interval. And thirdly, the function must have equal values at the endpoints of the interval. At the bottom of the slide, you can see a graphical representation of Rolle's theorem. It demonstrates that if a differentiable function f satisfies f a equals f b, then its derivative must be 0 at some point s between a and b. To better understand Rolle's theorem, let's consider its proof, which can be divided into two cases. In the first case, if the function is constant over the entire interval, then its derivative is 0 for all x within that interval. In the second case, if there exists a number d in the open interval where f d is not equal to f a, then we know that f x has both a maximum and minimum value on that interval. Since the function is differentiable everywhere, there is no possibility for its derivative to be undefined. Therefore, the maximum or minimum must occur at a point c where the derivative is equal to 0. Now, let me provide you with an example that demonstrates the application of Rolle's theorem. We are presented with the equation x to the power of 5 minus 3x plus 1 equals 0, and we need to show that it has exactly 3 real roots. In order to do so, we find the derivative of the equation, which is 5 times x to the power of 4 minus 3. Since this derivative is defined for all real values of x, its only critical points are where it equals 0. We find that there are two such points, x equals plus or minus 4th root of 3 divided by 5. Consequently, there can be at most 3 real roots of this equation, since Rolle's theorem guarantees that there must be a point with 0 derivative between every pair of roots. Additionally, there are at least 3 real roots as f x is continuous and changes sign at least 3 times without repeated root. You can verify this fact by examining the graph of f x at the bottom of the slide. Now, let's turn our attention to the centerpiece of our discussion, the mean value theorem itself. According to the mean value theorem, if a function is differentiable on an open interval and continuous on the corresponding closed interval, then there exists a value c within that open interval where the derivative at c will be equal to the slope of the secant line connecting the endpoints of the interval. In the center of the slide, you can observe an illustrative depiction of the mean value theorem. This theorem informs us that, for a function f x, there exists a point x equals c where the tangent line, with slope f prime of c, is parallel to the secant line connecting points a and b, with slope f b minus f a divided by b minus a. The proof of the mean value theorem involves constructing a new function g x, which represents the vertical distance between the graph of f and the secant line. Then, by applying Rolle's theorem to this new function g, we can show that there exists a point c where g prime of c equals 0. Substituting x equals c into our expression for g prime of x, we find that f prime of c equals f b minus f a divided by b minus a, which proves the mean value theorem. The mean value theorem enables us to draw conclusions regarding possible values of a function's derivative based on information about its values over an interval. However, it does not provide us with the specific value of c. Rather, it solely informs us that at least one value of c satisfies its conclusion. It is worth mentioning that Rolle's theorem is actually a special case of the mean value theorem. By assuming that f a equals f b, Applying the mean value theorem allows us to deduce Rolle's theorem. Now, allow me to present an example that demonstrates how we can effectively utilize the mean value theorem to solve problems. We are given a function f, x, equals x to the power of 3 plus 2x to the power of 2 minus x on the interval, -1, 2. We are tasked with determining all the numbers c that satisfy the conclusions of the mean value theorem. To accomplish this, we first find its derivative, which is 3 times x to the power of 2 plus 4x minus 1. Subsequently, we apply the mean value theorem to find that there exists a number c such that f prime of c equals f 2 minus f minus 1 divided by 2 minus 1. Solving this equation for c, we find that there are two possible values, c equals -4 plus or minus square root of 76 divided by 6. However, only one of these values falls within the given interval, hence the only desired value is c equals 0.7863. Next, let's consider another example that demonstrates how the mean value theorem can be utilized in problem solving. We are given a function f, x, that is both continuous and differentiable on 6, 15, where f, 6, equals -2 and f prime of x is less than or equal to 10. Our objective is to determine the largest possible value for f, 15. To achieve this, we apply the mean value theorem to find that there is a number c such that f prime of c equals f, 15, minus f, 6, divided by 15 minus 6. Since we know that f prime of x is less than or equal to 10 for all x within 6, 15, we can substitute the largest possible value of 10 for f prime of c. Solving the equation for f, 15, we find that the largest possible value is 88. Allow me to now provide you with one more example that showcases how we can utilize the mean value theorem to solve problems. In this scenario, we are given a function f, x, that is continuous and differentiable everywhere and has two roots. We are asked to demonstrate that its derivative must possess at least one root. To accomplish this, we denote the roots as a and b. Consequently, according to the mean value theorem, there exists a number c between a and b such that f prime of c equals f, b, minus f, a, divided by b minus a. Since a and b are roots of f, x, this simplifies to f prime of c equals 0. Therefore, f prime of x possesses a root at x equals c. Now, let's shift our focus to a practical example that involves a rock being dropped from a height of 100 feet. The function s, t, equals -16t squared plus 100 represents its position t seconds after being dropped until it reaches the ground. This problem consists of three parts. In the first part, we are required to determine the time it takes for the rock to hit the ground. To solve this, we set s, t, equal to 0 and solve for t. This yields the equation -16 times t squared plus 100 equals 0. Upon solving this equation for t, we find that t equals plus or minus 5/2 seconds. Since we are only interested in t values greater than or equal to 0, we deduce that the ball will hit the ground 5/2 seconds after being dropped. In the second part, we need to find the average velocity of the rock from when it is released to when it impacts the ground. To accomplish this, we employ the formula for average velocity, v sub a vg equals s of 5/2 minus s of 0 divided by 5/2 minus 0. By substituting the values, we obtain v sub a vg equals -40 feet per second. Lastly, the problem tasks us with finding the time t guaranteed by the mean value theorem when the instantaneous velocity of the rock is equal to its average velocity. According to the mean value theorem, there is guaranteed to be a point c within the interval where s prime of c equals -40. By taking the derivative of the position function s, t, we determine that s prime of t equals -32t. Consequently, the equation simplifies to s prime of c equals -32c equals -40. Upon solving for c, we find that c equals 5/4. Therefore, at 5/4 seconds after the rock is dropped, its instantaneous velocity equals its average velocity during its free fall, which is -40 feet per second. The figure displayed illustrates the velocity graph of the rock over time. At t equals 5/4 seconds, the velocity of the rock corresponds to its average velocity from the moment of release until it reaches the ground. Now, let's highlight two corollaries of the mean value theorem that are worth mentioning. The first corollary states that if a function has a derivative of 0 over an interval, then it must be constant over that interval. The proof of this corollary commences by acknowledging that since f is differentiable over I, it must also be continuous over I. We then assume that f, x, is not constant for all x in I. This implies that there exist 2 points a and b in I, where a is not equal to b and f, a, is not equal to f, b. We assume the notation such that a is less than b, which indicates that the fraction f, b, minus f, a, divided by b minus a is not equal to 0. Given that f is differentiable, applying the mean value theorem reveals the existence of a point c within the open interval from a to b where f prime of c equals the same fraction. Thus, there exists a point c in I such that f prime of c is not equal to 0, thereby contradicting our initial assumption that f prime of x equals 0 for all x in I. The second corollary asserts that if two functions possess equal derivatives over an interval, then they must differ by a constant over that interval. The proof of this corollary involves creating a new function h, x, equals f, x, minus g, x, then employing the first corollary to demonstrate that h, x, must be constant over the interval. And with that, we have concluded our presentation on the mean value theorem. I genuinely hope you found it informative and engaging. Thank you for your kind attention.